So a manufacturing company wishes to estimate the number of items that its workforce can produce on average each hour now that they have a new machine. The factory manager examined the records for a random sample of 10 hours over the past month, and those are in the table here. So using this information, we need to estimate a 90% confidence interval for the average number of items produced per hour, and we need to state any assumptions that we make. Alright, so I'm going to start this off by drawing a diagram of all the information we are given. So I'm going to start with a population, okay, and this population represents all of the hours in which items were made. Okay, so mu, we're not actually given, so this is the population mean, or the average number of items produced per hour, and this is what we're actually trying to work out with our confidence interval. So we could also have a standard deviation for that population. However, reading through this, we haven't actually been provided that information. So what we're doing though is we're drawing out a sample from the population, and that's these 10 hours worth of data. So that means that we have n is equal to 10. And since we're given the raw data, what we should be able to do is work out x bar, which is the mean of these values, and we should also be able to work out s, which is the standard deviation of those values. So before we get to that in a moment, let's just figure out what calculation we're going to need to do. So the information is needing to estimate a 90% confidence interval. So let's write that down. And it's for the average number of items produced per hour. So that's mu, or this population mean. So we have two kind of options in terms of the equation that we use to calculate it. One is in terms of z, and one is in terms of t. So the key piece of information to decide which way we go with that is this population standard deviation. And since we aren't actually given this, that tells us that we need to do the t distribution version, as opposed to if we were given the standard deviation, then we could use the z distribution version. Alright, so we don't have this, which means we're using t, and the equation is then the lower limit is minus t times sx, comma, and then the upper limit is where we have a plus, and it's again t from the t distribution times sx bar. Alright, so let's go and get our x bar and s from Excel. So I've copied in our information here. So we'll start with the mean of our sample. So it's going to be average in Excel, highlighting this across. And then we also want the standard deviation. And I'm going to pick this one here with the .s because it's based on a sample rather than the population. So again, just highlighting this, and we've got our result. Equally, you could get these from manual calculations or using your calculator as well. Alright, so marking in those values we just found out, so 161.2 for the mean and about 12.88 for the standard deviation. Alright, so the next thing I'm going to do is I'm going to make an assumption, and that's going to be that x bar, our sample mean, is normally distributed. And the reason I'm writing this out very explicitly is because our n, alright, the number in our sample, is less than 30. Now we can only usually make the assumption that x bar is normally distributed and say it's really valid when n is 30 or more, and we're well under that. Okay, so we need to really explicitly state that we are relying on this assumption, but consequently we may have some error in our results as a result of making this assumption. Alright, so moving forward with it though, what it means is we're going to be able to now calculate the standard deviation of our sample mean. So that's the sx bar that's required inside this confidence interval equation. So we can get it by taking s, our sample standard deviation here, and dividing it by the square root of n. So it's going to be the 12.88 divided by square root 10, and this is about 4.07. Alright, so the next thing that we need to think about is drawing ourselves a diagram so that we can find this t value. So scrolling down here. So we've assumed that our x bar here is like kind of normally distributed. And we're going to say for the purpose of figuring this confidence interval, right, the mean value of x bar is the sample mean. So that's that 161.2. And we need to determine these lower and upper bounds of x bar because that's the limits of our confidence interval. Now this time we said that we're going to use the t-distribution because we didn't know the standard deviation for our population. So when we move from x bar into t, we know that the mean value here goes to 0. And what we need to figure out is these limits out here on the t-scale. So we can use our confidence interval in order to make that happen. So we know that in here, this area needs to be equal to that confidence interval size, so 0.9. This means that the outer kind of sections have to make up the difference, and we know that the total under the curve is equal to 1. So that means that this is going to be 0.05 and this is going to be 0.05 because all three together add to 1. And again, you might see people write on the basis of this, alpha is equal to the difference between percentage terms. It's going to be 100% and 90%. So that would leave 10. So people sometimes say that this is then equal to alpha on 2 and alpha on 2. Of course, this is then gone to decimal form. Alright, so in a moment we're going to go and look up the t table, but what we're going to need to do that is an extra piece of information, and that is the degrees of freedom in our system. So we can calculate that with the equation n minus 1, where n is the number in our sample. And of course, if we scroll back up, we know that n is equal to 10. So that means it's 10 take 1, or 9 degrees of freedom. So before we do that, just remember in here that this is an area of 0.05, right? So these two pieces of information together, if we go over to our inverse t table, what we need to look up is the degrees of freedom. So we're interested in this row where it's equal to 9. And then the area in here, we just said a moment ago, was 0.05. So that's what each of these kind of columns correspond to. And 0.05 is this column here. So if we look at where these two intersect, it's at the 1.833. So that's the t-value here that we needed for our graph. So 1.833. So if I mark that here. And equivalently on the bottom end is just the negative of that. So 1.833 negative. Now we pretty much have all the information that we need to be able to figure out that confidence interval. Okay, we've got x bar, which was our sample mean of 161. The t-value that we need is where this mark is drawn, so the 1.833. And sx bar we calculated as this 4.07. So let's substitute that in. So our confidence interval is equal to, so 161.2 minus the t-value, times that 4.07, and then for the upper limit, oops, sorry, it just ends up with a positive value in here. So now it's just a case of typing it into a calculator, and we end up with about 153.7 and 168.7. So on the graph, that's these bottom and top points in terms of like the x bar kind of scale. Sorry. So 153.7 and 168.7. So that's the answer that the question was looking for. So the last little thing I want to write is how we interpret this. So what this is telling us is that we are 90% confident that the population mean, which is mu, is between our upper and lower points in our limit. So 153.7 and 168.7. And in the context of this question, these were like the number of items produced per hour. Cool. So that's pretty much all there is for this video, and I'll see you in another one.